this lecture is the first lecture, I believe, that you are going to have on CAD. Okay, so we are broadly going to have two lectures, introductory lectures in the area of CAD. One is digital CAD, and the other is a more new topic, which is analog CAD. So digital CAD has been there for quite some time, and it is the backbone of the digital chip design process. So let us first go through a few introductory remarks on what we are going to talk about here. First thing is, what is CAD? So full form of CAD, as we all know, is computer aided design, right? But design of what? So CAD is not just something that is relevant to the semiconductor industry. It is also used in a wide variety of domains. So it could be design of electronic circuits, which is popularly also referred to as the electronic design automation, or EDA, and then it could be mechanical and embedded systems such as automobiles and aircrafts. I believe you are aware of the fact that most of the controls in a modern automobile is computer controlled, right? Now in this connection, do you know which is the domain which is the largest customer for processors? So yeah, one would suspect that it's the desktop industry or the home computer industry. It's not that. It is the automotive industry, and the automotive industry uses a huge number of processors, and you know, a typical car can have up to 25 to 30 processors. Now why would it have so many processors? Does it do an enormous amount of computation to actually warrant that kind of computational power? Yeah, so what happens actually is, see, there are various parts in an automobile. Okay, so there is a power steering, there is a braking subsystem, there is the fuel injection, which decides how much of fuel has to be injected into your engine depending on the speed at which you are traveling and the road conditions, etc. Then there is a centralized door locking system, okay, which keeps track of which doors are open, which doors are closed, and which is child locked and which is not locked. So all of these subsystems are not manufactured by the automotive company, they are outsourced, and each of them comes back with its own processor, right? So as a result of that, you end up having a large number of processors, and then integrating them together into the same vehicle is a big problem. Why? Because now you don't have just one processor to deal with, but so many processors networked through a real time bus, because everything has to happen in real time. Suppose you detect a crash and the airbags have to come out. So that entire process from capturing the image, processing the image to detect the crash, then collapsing the power steering, and then blowing up the airbag, okay, and the steering has to go back in a collapse, and then the airbag has to come out. Whole thing has to happen within a fixed window of time, right? So it's an enormous challenge to put these things together, and sometimes peculiar kinds of mistakes happen. So there was an instance in one of the very renowned car companies. One of their vehicles had this problem that when the driver would pull back his seat, then the CD player would start ejecting all the CDs. So this is an integration problem, right? So there is an enormous requirement for computer aided design. You want to design things in such a way that they are correct and verifiable, and then finally we actually take it to implementation. A similar scenario exists for large software systems also. There also we need CAD. Why? Because there are too many components, too many pieces of code written by, I mean, a variety of different people across the globe, right? Again, when you try to put them together, they may not work properly, and moreover they can be distributed software, they can be concurrent software, okay, they may be running on multi-core machines, in which case they can be multi-threaded software, right? So there are so many different paradigms that has to come together that it becomes a difficult thing. So people use tools to model the software at a higher level of abstraction, and then progressively they verify the software at that level of abstraction and then go into the development of the actual software components. Why do we need CAD? We need CAD because the design sizes are growing and it is becoming too complex to be developed manually. Now, when we were in our second year in the computer science department, as part of the switching lab, we were asked to develop a small CPU, okay, on the breadboard. So, putting together your adder, your multipliers, the registers, okay, program counter, everything on the breadboard, connect them together and make it work. Okay. Now, the design which I did was the only one which worked, and it only executed the NOP instruction. That's because there are a lot of other things that come up. When you have a reasonably large size and cramped circuit on the breadboard, problems of noise and clock frequencies and all those kinds of things come up, which you don't realize when you do a textbook study of the thing. So, that is only a few chips, right? Now, today we are trying to integrate multiple processors on the same chip. Can you imagine how many processors we are trying to integrate today? If you look at a Cisco router chip, it can have up to 200 processors on one chip, right? And there is a project being funded by Sun in one of the universities in US, which is targeting to integrate 1,000 Spark cores on a single chip. Okay. So, that is the kind of integration that we are talking about, and obviously manually doing that kind of thing is out of the question. The other thing that we need is we need design space exploration and optimization, because if you do things manually, you will not be able to optimize it to the extent that we need. So, that is another very important thing. We need to explore what are the possible ways of doing the design, and then from that optimize and choose the best solution. And we need to verify the design before implementing it. This is a very important thing. Today, in many areas we have more computational power than we require. Typical example is the desktop, where we would typically most people would be using them for office purposes, like PowerPoint, Excel, and Word, and a few other applications, mail and things like that. But the amount of power that the processors give you is much more than, you can do a lot more computation than that. So, the problem is not in scaling things up there, the problem is making things in a more verifiable way. So, we want to grow, but we do not want to make too many mistakes while growing that. So, that verification problem is a major problem, and we are going to talk about that later. How does CAD work? So, the design is entered in some language. It could be a graphical language, you can draw using symbols, or it could be a textual language, where you actually have a language in which you enter it like a program, and the CAD tools will take that as the input and perform design optimization and verification. Okay. And also in many cases we will have automated or manually automated in the which we can call semi-automated ways of synthesizing the design from the specification that you have entered in that language. So, this shows the flow. Now, we are going into digital CAD. Okay. So, this is the flow which I talked about in the first lecture, that from concept to market there are 4 major areas. The first one is that we go from specification, where we specify what we want to design, then we have the implementation, and then from there we build a hardware prototype typically, and then finally we go for manufacturing. This is pre-silicon, this is post-silicon. In this part, in the first 3 steps, we do design synthesis and validation. So, progressively we synthesize the design and verify that the design is correct. And in the lower 2, because we are in the post-silicon area, we have to test that the silicon is correct. So, that is manufacturing and testing. So, again let us reiterate what are the challenges that we have to look at in the CAD area. So again we return to the example of designing a pacemaker. So we need to minimize delay. So delay optimization algorithms has to be there. We need to have algorithms which can synthesize the logic and minimize the delay in the logic. What is the delay in the logic? The number of logic stages that you have, right? That is a combinational delay. So if you have a 5-stage circuit in which you have 5 layers of gates, then the delay is proportionate to that. And then there is a sequential delay also. In how many clock cycles can I perform this multiplication? Okay, so that's the sequential delay. May not be done in one cycle, but you may need multiple cycles, right? So delay optimization algorithms is one thing. Then at the same time, we don't want to, you can design circuits which have very less delay, but then the area of that is going to go up because the number of gates that you will need is going to be much more. So again, we don't want to go to that extreme. So we want to optimize the area also. I have more integration, more compact circuits. Then we want to do power optimization. So you can have a very fast circuit using a technology which eats up a lot of power. But if you reduce the power, then you may have a slower circuit. So how do we balance these things to get a balance between area, delay and power? Then improve verifiability. We need to make circuits more verifiable. We need to make the manufacturing process more reliable so that the number of defects in the chips that we manufacture is not very high, right? Now as you go for more and more compaction, as you reduce the transistor geometry, the chances of error in the fabrication grows, right? So you need to see how to tackle that effect. So there are various options. For example, you may have redundancy in your circuit. If it is a very critical circuit, you may have the same component replicated in 3 different places, and then you take the majority of the output of the 3 to decide what is the correct output. Okay, so there are various options that people do, or you actually sacrifice a little bit of the area and make your transistors a little bit larger and improve the yield of the fabrication process. And then test automation and design for test. So this is another major area in CAD, that how do you have algorithms for finding out the minimum set of test vectors by which you can cover all the faults in the circuit. So you start with a fault model and say that these are the possible faults, and then let me see that which test is actually going to sensitize that fault, right? Do you understand what I am saying by sensitizing the fault? No, right? So let's say that you have an AND gate, right? And suppose you have an AND gate, and suppose you want to find out that is this output stuck at 0? Is it stuck at 0? Right? Now, if you give an input 0 0, will it be able to detect that? No, because the output is expected to be 0, so you don't know whether it is stuck at 0. If you give it 0 1, no. So what is the vector which is actually going to produce this? 1 1. Okay. So 1 1. So 1 1 can detect a stuck at 0 fault here. And let's say that the same 2 are actually going into an OR gate, and you want to check whether this is stuck at 1. Now is this vector going to show you that? No. So you need one more, right? So you need a 1 0 or a 0 1 or 0 0. Yes. So 1 0 0 1 0 will not. So we need 2 vectors, 1 1 and 0 0, right? So in a large circuit, the challenge is to determine that what is the minimum set of test vectors by which you are able to sensitize all of these faults, right? And then it's not just sensitizing the fault, it has to be propagated up to the output, because here the fault that I was examining was at the output, right? But the fault may be somewhere in between. There may be a combination logic here, and then the output of this gate is going into another combinational logic, right? And then if I want to check a fault here, then I need a test which is actually going to sensitize this fault, and then that test should also carry the fault right up to the output, and some valid output in the valid value in the output should change if the fault is present. Okay. So, that is the challenge in designing a test suite, and there are various algorithms, there are various new kinds of challenges that are there. And then again at the top of all this, we want to reduce cost. So, there are we have to design CAD algorithms which can do things in such a way that the total cost of the thing goes down. Now, let us look at the levels of abstraction at which people do this design in digital CAD. So, at the lowest layer we have the transistor level, okay, where we have CMOS, PMOS and NMOS transistors. Then above that we have the gate level. Now, please look at the corresponding things here, the formalisms that by which we specify what we want. So, at the lowest layer we have schematic. Now, what is a schematic? A schematic actually specifies the gate, drain and source connectivities of the different transistors, which is connected to what, and it also tells you the geometries of these transistors, what are the width and height of these transistors. Okay. When you go one layer up, you are now in the Boolean logic domain. So, you have Boolean, you specify these gates which are actually Boolean functions, and you have also flip flops which encode memory, and so the formalisms here are Boolean logic and finite state machines. Okay. Now, today entering your design at this level is too complex. We can't take a processor and enter the design at the gate level. So, you cannot manually say that these are the gates of the processor and this is how they are connected. So, we need to go at a higher level of abstraction. What is the higher level of abstraction? The next higher level of abstraction is the what we call the register transfer level. So, here we use languages like Verilog, VHDL or System Verilog, where the language is a restricted semantics of programming languages by which you can express communicating concurrent state machines. So, it is not just programming language which supports procedural code of a single process, but it is actually set of communicating concurrent state machines. So, for example, when you write always at passage clock, it means that this block is going to get triggered when there is a positive edge of the clock, which means when the clock goes from 0 to 1, then we do this. And what do we do? If not reset, then we assign A2 to A1, and then otherwise yes, we assign A2 to A1 and then assign not of A1 to A2. Okay. So, this is what it does when at every passage of the clock, right. So, this is a very primitive form of Verilog code. Okay. You will learn more of the Verilog during this course. So, you enter the design at this level, and then you have a design compiler which is going to take this and produce the gate level design, and then again you have a compiler which is going to take the gate level design and then produce the transistor level design. So, it is in this hierarchy that we have to do the design. Now, what are the verification problems side by side with this? When you first enter the RTL, this is the place where you are likely to make most of the logical bugs. See, you had something in your mind, but when you coded it in Verilog, the design is doing something else. How would you know that the design is correct? Right? So, that is the verification problem at the topmost level of the design hierarchy. Then you have the translator which translates this to the gate level. So, you want to verify whether what you wrote down here in RTL is actually what the gate level does, right. Now, the tools which do these translations for you from the RTL to the gate and the gate to the transistor, they have been in operation for so many years now that you have started depending on these. So, they are almost correct by construction. But new issues are coming up here. It is not about functional correctness. It is not about whether this is functionally implying this and this is functionally implying this. It is about the other issues like timing, like power. Those things are not yet at a good enough level to be automatically synthesized down the same design flow, and these are the areas where new CAD problems are coming up. That how do we do power aware synthesis, how do we do timing aware synthesis, how do we take care of the different problems that we are seeing at the post silicon level, how do we actually tackle those in the pre silicon verification. So I will give you some examples of that. Let us take this example to demonstrate these steps. So we start with what is called a 2-bit gray counter. What is a gray counter? A gray counter is going to count through a set of numbers in such a way that successive values will differ only in 1 bit. Okay, so they will differ only in 1 bit. So this is the important thing. The reset signal. So this is a gray counter which a reset. The reset signal resets the counter to 0. So if you look at the state machine representation, so the state machine representation says that initially the counter is in 0 0. Okay, then if I do not reset it, so this blue arrows actually indicate the normal operation of the counter. So 0 0 to 0 1, 0 1 to 1 1, 1 1 to 1 0, and 1 0 to 0 0. And you see that successive values like 0 0 and 0 1 differ in only 1 bit. 0 1 and 1 1 differ in only 1 bit. Okay, and if you have a reset in any of these states, then it reverts back to the 0 0 state. Okay. Yes. So 0 0 can't go to 1 0 because that also differs in 1 bit. No, this is one implementation of the gray counter. So you could have gone exactly the opposite way around, 0 0 1 0 1 1 0 1. The counter is going to count through all 4 of these values. Okay, it is going to cover all 4 of these values in a cycle and then again repeat that. So you could have gone this way or you could have gone this way also. Are you getting it? Right. So now, given that this is the state machine representation of what we want to do, of the counter that we want to implement, we have to somehow translate this into the final gate level and transistor level implementation, right. So the first thing that we could do is we can draw the state transition table for that. So what does the state transition table show you? So if I am in state 0 0 and if reset is 0, then I go to 0 1. So 0 0, reset is 0, then I am going to 0 1. If I am in state 0 0 and reset is 1, then I stay in 0 0. Okay. If I am in 0 1 and reset is 0, then I am going to 1 1. So 0 1, if reset is 0, then I am going to 1 1. Okay. So I have the present state, the reset, and the next state. Okay. So this is the state transition table. Now from this state transition table, let us see what we can do. We will develop the state transition functions from this. So how do we do that? We look at this column corresponding to N0 first. Let us look at the column corresponding to N0. So that is this column. Okay. Let us find out that in this column, where do we have 1? So we have a 1 here and we have a 1 here. Okay. Now when do we have a 1 here? When S0 is 0, S1 is 1 and reset is 0. So that is what we have written here, S0 dash S1 R dash. Okay. Now let us look at this one. S0 is 1, S1 is 1 and reset is 0. So S0 is 1, S1 is 1 and reset is 0. Okay. So the first state bit becomes 1 in the next state only under these two conditions, that is this one and this one. Only under these two cases does the next state become 1. This bit of the next state becomes 1. So this is one of the state transition functions, which tells us that what is the state bit 0 going to look like in the next state. Okay. And then similarly we do the same thing for the state bit 1, for which I look at the places where it has become 1. This is where it is 1, this is where it is 1, and then I look at this is all zeros, so all zeros, and then this is 0 1 0, so S0 dash S1 R dash, S0 dash S1 R dash, right. Okay. Now this is not optimized, we can further optimize this to get this, right. Now that you can see, because you can see that if I take S1 R dash as common in these two, then I get S0 dash plus S0, which is 1, right. So it minimizes to this. So after logic minimization I have these two, right. Then these are the state transition functions, and I develop a Verilog code to express it. So what do? I write module gray counter, these are the state bits S0 S1, and this is the reset input. So see, the module is like a box which has the three the RST as the input, which is declared as an input here, RST is an input, and then you have S0 and S1 which are declared as registers. Okay. And then okay, I just missed the clock, so clock should also be here as part of the argument. Okay, I missed that here. So another argument of this module will be the clock. And then what we do is we do that always at passage clock, whenever the clock transits from 0 to 1, we do the following thing. See, S0 less than equal to S1 and not RST. This less than equal to is a kind of assignment. Okay. So there is a meaning of this assignment. This meaning of this assignment is that this assignment will take place at the end of the simulation cycle. Okay. The semantics of this assignment, which is called non-blocking assignment, will be taken up in the lectures on Verilog. Okay. So effectively what it means is that if I have S1 and not RST, if I have S1 and not RST, then in the next cycle S0 will be high. So I take the truth of S1 and not RST and assign it to S0 in the next cycle, right. So that's what this one was saying, that if S1 is high and the reset is low, then in the next cycle N0 should be high. So N0 is what? It's the same state bit, S0 in the next cycle. Similarly we write this one is encoded here. Okay. Now what the tool is going to do, the design compiler, it's going to take this code and actually give you the circuit. So that is the steps of synthesis. So it synthesizes this circuit and produces it implements it with 2 flops, 2 gates, and as you can see that it's implementing the same logic, because if you look at S0, then what is the value that it is getting? It is S1 and not RST. So RST is negated here, and S1 and not RST is feeding into the input of this flip flop. So when the passage clock comes, then that is going to get latched, and that value is going to show up as the next value of S0. Okay, I think we went through the whole process a little bit fast, but I am sure that in the lectures that you go through on Verilog, you are going to have more time, more exposure, and then you will actually do some of these designs yourself in the lab to get comfortable with this process. So what then are the levels of abstraction that in which we are doing things? So at the top we have the system level, which I have not shown. The system level is where you actually design something for a whole platform involving several chips. Okay. Then you have the chip level, and then you have the register transfer level, the gate level, the circuit level, and the silicon level. So typically today the design is entered at this level, at the register transfer level using RTL. Okay. People are trying to migrate the design entry to higher levels. They are looking at new kind of languages, okay, where you can enter the design at a higher level of abstraction and then compile it from there. So, things like System C is one candidate here. Okay. Then there are new versions of, there are new entries like BlueSpec, Verilog. There is a language called Spec C. So these are the things that people are trying to do, but so far they are mainly modeling languages. They are used for modeling the design at the system and the chip level, making sure that whatever you intend to design there is correct. But then from there, what you do is you actually pass an English document to the designer, and the designer uses that to start coding the register transfer level version of the circuit. So let us just look at each of these levels in using some pictures. So this is the silicon level. So I think in the last class you have seen some of these. This is a CMOS inverter at the silicon level. If we go one level up, then we have this schematic level for the CMOS inverter. Then we have the gate level. This is the register transfer level. So in the register transfer level, you see that we are using blocks. Okay, so these blocks can have registers, they can have logic, they can be logic blocks designed by somebody else, which you actually incorporate in your design. Okay, so at that level, you have two main things. One is the controller or the control path, and the other is the data path. What is the data path? The data path is the flow of the data through the different registers, right. So in a processor, for example, your operands are getting loaded into some registers, then it is passing through the arithmetic processing unit, and then it's going back to some register. So the path that the data follows is called the data path. And who actually controls the flow of the data through that data path? It is a controller. Okay. So the task of the synthesizer is to take the register transfer level description, extract out the control and the data path, synthesize the data path and the controller as separate entities, and then integrate them together to get the overall design of the chip. So it's a completely non-trivial process, and let us we'll go through that once. Then we have the platform level. So we normally, you may not find too many lectures on this being delivered in a computer architecture course, because we typically go up to the processor level, but we do not often talk about what is the platform level beyond that. So this is the Intel processor plus chipset platform architecture. So this is the processor sitting up here. Okay, so this is a Pentium processor. Okay, and then how many of you have actually opened up a PC to see how it looks like inside? Oh, I'm happy, very happy, because I mean, previously I would imagine that only a couple of students would raise their hands. So I did not expect that so many of you have actually done that. So if you open it up, then you will see these other chips. Okay, so this is a Pentium. So this is a memory controller hub. Okay, so now the processor typically communicates with the memory using a very high speed bus, and the other IO devices, etc., they are not linked into that bus because they do not have that speed. Okay, so their communication with them is done through a low performance bus. So most of the platform architectures will have a high performance communication architecture and a low performance communication architecture. So in this case, you have this high performance bus which actually connects the memories. So these are the memory banks, and they are connected with the processor through this memory controller hub. Okay, and then from this you actually have a connection to the low performance communication, the communication medium, where you have these other devices. What are these other devices? These are the PCI slots, these are the USB devices which you can connect. So when you connect an USB device, it is actually going to go through the I/O controller hub through this high performance bus and then actually to the CPU, right. So it doesn't, it's not directly hooked up here. And then you have the Ethernet here, you have the disk drives here, the CD drives here, and you have the audio channels. Okay, so all these they sit on the I/O controller hub. Okay, so this is the complete platform level. Now, this platform level, at this platform level also we have a lot of CAD problems. What kind of CAD problems do we have there? First of all is designing this. Okay, the second thing is that we want to do a lot of platform level power management, okay, because at all the time all these devices are not in use, right. So we want to switch off the ones which are not being used by having a platform wide power manager. Okay, so that is a new area in which a lot of research is taking place. How do you do efficient platform power management? And the picture is completely different, I mean at least in terms of performance, when you take the similar picture for a mobile processor plus chipset architecture. This is for a typical desktop. For a mobile device like a cell phone, you will again have a different kind of architecture at the platform level, and there power is a very important criteria. I am missing that. I don't know. So I have to check up and let you know. Okay, this is a chart which talks about the 3 different aspects of the design. So you have the behavioral dimension, you have the structural dimension, and you have the geometric dimension. So as you can see that at the behavioral level, at the top you have the system. The system is the entire thing that you want to develop on top of your computing platform. From that you have the algorithms. Okay, what kind of algorithms? The algorithms could be a very high level algorithm like a sorting algorithm which you want to implement in hardware directly as an ASIC, or it could be an algorithm for multiplication, for example. It could be a division algorithm which you want to implement in hardware. And then you have the register transfer level description of the circuit, then you have the logic level, and then you have the transfer functions at the transistor level. Okay. On the structural side, what do you have at the systems level? You have the CPU, memory, etc. At the algorithms corresponding to that, you have the subsystems and buses. At the register transfer level, you have the registers, you have the ALUs and the combinational logic. At the logic level, you have only gates and flip-flops. And at the transfer function level, you have the transistors. So these transfer functions are actually the equations which, for example, a SPICE simulator would be using. Okay. If you look at the geometric side of it, then at the top level, when we are talking about CPU and memory, etc., we partition them in geometry as physical entities. They are chips and physical partitions. So the platform that you saw in the last slide is actually a geometric view of the CPU, memory, etc. interaction. Okay. So how do we place that? So that is also an important problem, right? So it's starting from PCB layout to the layout on the chip. Okay, where you want to place your different blocks is a geometric problem. Then you have clusters corresponding to the subsystems and buses. So on the chip, you can have several clusters of devices, right? Then at the register transfer level, you have the macros and the floor plans. We are going to talk about that. At the logic level, for the gates and flip-flops, you have cells. These cells are the standard building blocks of a digital design, and you can also have plans for modules. And at the transistor level, we just deal with polygons. The polygons that actually talk about the layout of the transistor in terms of the MOS, the metal, etc. So we are going to quickly go through the steps of these. So the digital design flow from simulation to synthesis to place and route to the final manufacturing. So let us see what are the challenges there. So the first thing is high level synthesis. What is high level synthesis? I take a description in Verilog and VHDL, then there is a design analyzer. This design analyzer parses that the circuit description. Okay. So it's a compiler or the parser for Verilog, VHDL or system Verilog, but it also does a lot more. It creates what is called a control flow, control and data flow graph. So it actually takes care of what is the sequence of operations that you are doing in your RTL and builds a graph from that. That graph is then used to do the scheduling, allocation and binding, which are the main steps of high level synthesis. And the outcome of that is you have the data path, which talks about the way the data is flowing through the registers and the combinational logic, and you have the controller, which actually controls the data flow through that data path. Okay. So let's go through the first step. So suppose in somewhere in your logic, in some module, you have written these steps. So you have written that E is equal to A plus B, then you have written G is equal to A plus C, then you have written F equal to C plus D and H equal to D plus A. This is some arithmetic operations that you have written in your Verilog code. Now the corresponding graph that is built out of this, just to give you a toy example, is like this, that you see that this E is A plus B and then your G is E plus A, okay, and then similarly you have C plus D is F and then F plus D is H, okay. So this is what I mean as the control and data flow graph. So this is a simple example. Now the next step is to schedule these operators. So what do I mean by scheduling these operators? You look at this thing. Can I perform this with one adder? I can. What do I have to do for performing this with one adder? Store E, in the next cycle use the same adder to add E and A, store G. In the next cycle use the same thing. How many clock cycles will I require for that? How many addition cycles will I require? 4, right? How many are we requiring here? If we use 2 adders? 2. If I give you 3 adders, can you make it better? No, because anyway you have to add these 2 first and then use the result in the third adder, right? What you could do, however, is take one adder and fit in A and B into it, and then take the output of that adder, fit it into the other adder, and then use A and E to go there, take G out of this, right? Now you may say that this whole thing can execute in one clock cycle, but that's going to do what? That's going to make your clock cycle width larger, right? Now making your clock cycle width larger may actually slow down several other parts of the circuit which could have actually worked using a faster clock, right? So now look at the problem. You have a huge circuit, different parts of that circuit can work in different speeds. Your job is to find out what should be the clock speed so that the overall thing works the fastest, right? Now if you put in too much of combination and logic between the clock pulses, then the clock width will grow and it is going to slow down other parts of the circuit. If you make the clock pulse narrower, then you cannot push too many combination and logic one after the other, right? So you will need more number of cycles, but how do you gain from that? You can reuse the same set of resources, because then I will not need these 2 adders. I will do both of these with one adder, like I have done here. I have used the same adder twice, right? Now that is actually keeping the number of adders down to 2, right? So as you can see, there is a trade-off between the clock width, the area, the delay, everything together. Okay? So this is just to give you an intuition. The formal algorithms of how you tackle all these things together is what you will learn in the lectures on CAD. So this one shows you 3 different schedules for this operator graph. So the graph, this is the operator graph. The graph that you saw in the last page was another operator graph. So here we have these operations that we have to do, and these are the additions and these are the multiplications. Right? For the time being, let us make a simplifying assumption that addition and multiplication will require the same amount of time. Okay? So both of them can be done in one clock cycle. Let's see. So this one, as you can see, uses 2 multipliers and 2 adders, but completes the whole thing in 4 clock cycles. Right? If I reschedule the operations, then I can have a schedule which uses only 1 adder and 2 multipliers. This is this one, but it requires how many? 5 clock cycles. And the last one does everything with only 1 adder and 1 multiplier, but it requires 1, 2, 3, 4, 5, 6, 7, 8 clock pulses. Right? So there is a trade-off between these two, the number of cycles, which is the speed, and the number of resources that you want to use. Right? So you want to do this trade-off based on the entire set of operations that you have to do. By the way, where are these things coming from? These operator graphs. Think of a processor. For every instruction execution, there is a set of arithmetic operations. So for every instruction execution, you can say that these are my micro instructions, micro operations that has to be performed. That is going to give you a graph like this, right? And then you want to, find out that how many of those resources like adders, multipliers you need on the processor, so that you are able to do this in the minimum number of clock cycles using the minimum number of resources. So strike a balance between the two and then go for that design. The next problem is allocation and binding. So far what we were deciding is that how many of those adders and multipliers are we going to need, right? Then that task of doing that is allocation. Allocate this many number of multipliers, this many number of adders, and the thing that we did not discuss there is how many registers do we need, because as you can see that if I actually want to do these two with the same adder, then I need to store E somewhere, right? So I will need registers for that. So how many registers am I going to need? So in this one, as you can see that this shows a typical allocation and binding. So we have decided that we will do this with 2 adders, adder 1 and adder 2. We are going to allocate these 2 additions to this adder and these 2 additions to this adder. Okay, and then we will work with 4 registers. Now see that we have to bind the variables to the registers, right? So A is bound to register R1, B, E and G are bound to register R2. Now what is the criteria for binding these on the same register? They should not have to be present at the same time, because then they will get overwritten. So you see, in the first cycle I need B as the input, but and E is going to come as the output of this. So in the first cycle what's going to happen? I will have A here, I will have B here, E will come as an output here, and then in the next clock pulse I can latch E into this register. And I can do that because I don't need B anymore. I don't need B anymore in the next cycle. So I can use the same register to store E. But I can't overwrite A because I need A in the next cycle. So in the next cycle I will take A and E and I will produce G here, and then G will get latched on to the same register in the second cycle, right? Why? Because at that time I don't need E anymore, so I can just latch G into it. So this is the act of binding, that which are the variables which are getting bound to which registers, right? and we want to reduce the number of registers. So what do we do? So there is a very nice problem. So you take each variable and note down the time period for which they are active, the number of cycles for which they are needed. So let's say that this is my time. So I need A from here to here, and this is not this example. So let me use some other variable names. So I need A from here to here, I need X from here to here, okay. I need B from here to here, okay, and I need C from here to here. The question is, how many registers will I need? Right. So 3 is unavoidable here, right? But if I have, how many am I going to need now? Still 3, right? So there is a nice algorithm which actually treats these as nodes of a graph and then puts an edge. So I denote A as a node, I denote X as a node, and I put an edge between A and X if they overlap somewhere in time, okay. And then I put with X and C, I have an edge. Between X and B there is an edge, okay. So I build a graph like this, and then I color this graph. What is the coloring of a graph? I will add colors to the nodes of the graph in such a way that adjacent vertices will never receive the same color, right. Why will adjacent vertices should not receive the same color? Because you cannot use the same register if there is an overlap in time, in their lifetime. So you cannot use the same register. And then you ask, what is the minimum number of colors that I need to color this graph, right. So that's a graph coloring problem. The graph coloring problem in general is an NP complete problem, but for this category of graphs it is polytime solvable, right. So you have a polynomial time algorithm from graph theory to solve this problem and find out what is the minimum number of registers that you would require, okay. So there are nice little problems, taken from here and there, which people use in CAD. You will see the area delay trade-off in the lower level logic synthesis also, okay. So for example, this is the same circuit, F is A plus B times C plus DE, okay, A plus A or B and C or DE actually. So this is an implementation of this logic using 5 gates, right. This is 5 gates, and the delay is 2 because this is one stage, this is one stage, okay. So in terms of the number of gate stages, the delay is 2. The another implementation of the same circuit, I have a delay of 3, but the number of gates now is 4. I think in both cases I missed the leading gate, that's why I have this. Now the number of gates is 4. So you see here this requires lesser area, but because there are more number of stages, so the delay is more, right. Now it is not always the case that your criteria for optimization is to minimize one of these. In different parts of the circuit you may choose to do different things. In some parts you may want to reduce the delay, in some other part you may want to reduce the area, okay, depending on how much time critical the logic in those parts are. And there are nice algorithms which do this for you. Now after synthesis, after these steps of synthesis, what you have is, for each module that you have synthesized, you have certain geometries. So you have for module A that I have synthesized it into a box of width 1 and height 1. Module B is width 1 and height 3, okay. The next step is to place them on the chip floor. Now this is again a nice geometric problem. So this shows 3 different ways of placing the same set of blocks, okay. Which of them are we going to choose? What decides the choice among these? So one thing is that we want to do them in as compact way as possible. Now all three of them are very compact. Now this is a very utopian situation. Typically you will find that you cannot pack them so tightly and there are gaps, right, between the blocks that you place. So you will find that in general there will be gaps like that. Now the question is, how do we, what makes us choose between these if they are all very nicely and compactly mapped? What actually makes us choose between them are several features. One is routing. Now see, these blocks, these modules are going to be interconnected, right? So you can think of each of these blocks as having several pins. So let us say that block B has these pins, okay, and let's say block A has these pins, and then this pin of block B has to be connected to this pin of block A, this pin of block A has to be connected to this pin of block D, okay. Now this one of E has to be connected to this one of D, right. Now you see the problem, right. So there will be a pair of modules which have a lot of interconnections. So it is better to place them close by, so that you are able to route them, route the connections between them easily. And if you place them too far apart, then the interconnect is going to eat up a lot of your space. And this whole design cycle, the design cycle where you actually manually do this thing, more than 30% of that is spent in actually planning the interconnection. It's a real big problem. And today people even try to think of interconnections well before you have actually started designing these blocks. You first start thinking, what are my blocks, where am I going to place them, how am I going to route them, right. Then you start actually saying that, okay, this block has to be designed with this geometry. So you ask the synthesis tool that design it in such a way that it fits into the budgeted box, okay. The other important thing that we need to look at here is the power. So if you find that these two, for example, are two processor cores, then this is a very bad placement, because the region here is going to get really hot, because the processors are active. They are going to eat up a lot of power, and the power dissipation near the boundaries is better because it gets dissipated outside the chip. But here between the two processors, the power dissipation cannot take place, right. So it's going to really heat it up very badly. Then you might say that, okay, if that is my situation, then it is better to place E and D well apart. So it might be that your A and C are two cache blocks, so you place A and C here, and then push E and D too far away place. So it's not just in terms of compactness and routing, we have power also as another issue, right. So these are the constraints that go into the floor planning part of it. After you have done floor planning, then you have to do the routing, the actual routing of that. Now there are various ways in which people do routing. There are, for example, matrix based routing algorithms. So you say that, okay, I am going to have the chip, these are two modules, this one has these pins, this one has these pins, and I am going to do routing with only two layers. So what am I going to do? I am going to support only horizontal and vertical wires. So I have to connect this with this, so I will connect it like this, right. Now if I have to connect this A with this A, how do I connect it? So what happens there in two layer routing is that you say that these ones, the ones which are vertical, they are in one layer of the chip, and this one, the horizontal one, is in another layer of the chip, and there is a via, the thing which we call the via, which is what, which is a connection which goes from one layer of the chip into the other layer of the chip. So do you get what I say? So these two are in two different planes, and there is a connection which goes from here to the other through a hole here. Okay, so that's a via. Now if you choose that, then you can do this. Why? There is no problem here because this and this are not actually intersecting. This is in one layer, this is in the other layer. So they are not intersecting, but you can connect them, right? The question is, given any kind of thing like this, is it possible to route between every vertex to every other vertex using only 2 layers? The answer is yes. You can do everything with just 2 layers, right? Now that's kind of nice, right? So we say that only with 2 layers. But what is the trade-off with just 2 layers? The number of the space that you require for the routing will grow, right? Because the next time now when you want to connect this with this, okay, how are we going to connect it? Can we just reuse some of these? No. So we will have to again go something like this. So that's bad. Now we have 3 channels. This is one channel, this is one channel, this is one channel, right? So it's going to grow as the number of as the net interconnection becomes more complex. So people are looking at many other ways of routing also, not just in channels like this between the modules. You can even use the space on top of individual blocks to do the routing. So let's say that the blocks are placed here and we use one layer above that to do the routing, right? So that's called over the cell routing. And think there are many different algorithms for doing this and many different kinds of technology. And this is how it looks like after your routing is done. Okay, so the blue wires are the nets are which are the connections. Okay, so I mean this is mind boggling, and obviously you can see that doing it manually is quite out of the question, right? So CAD does this for you. Okay, now let us come to the topic on verification. So far we have only talked about the design flow, but 70% of the actual design time from the concept of the chip to its actual productization is spent in verification. 70%, and it is growing. It is growing. So if you look at this picture, this is a picture which was published by a company called Zero in Design Automation, which was a company which was started by Professor David Dill of Stanford University. So he started a company on verification on this. So anyway, so this shows that look, simulation is going to eat up 46% of the time, right? That's what it uses up today. And then you have other types of verification at various places, like you have timing analysis, you have equivalence checking, which I'm going to talk about a little bit, and then you have the design. Okay, so in the design you have block level simulation, you have the architectural simulation. So the first thing is that when you start designing a very big chip like a processor or a really big digital design, then we start with what is called an architectural specification. These are developed by people who are called micro architects. What do micro architects do? They decide on the architecture of the chip. What do you mean by the architecture? What is the instruction set? What are the different addressing modes? How are you going to manage the access of the caches? How do you do resource arbitration between the different blocks which are going to access the cache or access the bus or whatever? So all these things, this planning is called developing the architecture of the design. And today most of the novel innovations in the digital chip design takes place at this level, at the architecture level. People come up with new ideas. Like for example, the initial processors did not have pipeline. Then pipelining was brought in. So it was said that why do we fetch one instruction at a time? While we are executing the next instruction, let us fetch the, while we are executing one instruction, why don't we fetch the next instruction? Then people started saying that when we are executing one instruction, why don't we start the execution of the next one, right? If you have an if then else branch and you don't know which way the program will go, can we start executing both of the branches, pre-executing both of them, and then when we finally know the outcome of that branch, we will flush out one and then proceed with the other, right. So all this management, that which instructions are being fetched, how are they piped through the processor, this is architectural design, and there is an enormous amount of opportunity to do that today, because we are going from one processor to 2 processors on a chip to 4 processors on a chip and to the next generation 1000 processors on a chip, right. How are we going to manage the architecture of this? So that's an enormous task, and the micro architects are the people who actually do this part, but they do not like the verification people, because the verification people say find out that loopholes in the architectures. Now if you find those loopholes in the architecture after doing the whole design, then that's very bad, right. It's an embarrassment for everyone. So you want to make sure that the architecture is correct. So what you do is you develop executable models of this using languages like C, System C or Stral, or there are a host of other different languages, and make sure that this is correct. This is something which is done, but then at the end of it, what do? You produce a component specification document. You produce the document, the microarchitectural document of the different architectural blocks of the system, right, and that is an English language document, right. Now this is where a lot of thing is going on, that how do we make this more formal, because what happens is that when you document it in English and when the designer actually reads it for keying in the RTL, he may interpret it in a different way, right. So there is a lot of gap between what the microarchitect actually intended and what the chip actually does, right. So that is a gap that needs to be addressed. Anyway, so once you have the specification document, that is used as a reference for coding the RTL. So then you start writing the code for the different RTL blocks. So you use Verilog, VHDL, system Verilog, etc. And then when you have written down the RTL, you integrate all the RTL blocks together, put in all the modules together, and then you do a validation of the implementation, where you actually check whether the RTL does what the microarchitect intended to do. And then once you have done that validation, then you go for synthesis of that into a gate level netlist, and then from the gate level netlist you have tools for generating the transistor level schematic. At these levels we do what is called equivalence checking. We need to check whether the RTL is equivalent to the gate level design, the gate level is equivalent to the transistor level design. Now see, here what is the equivalence? The equivalence is based on Boolean logic. Are they equivalent with respect to Boolean logic? So are their Boolean functions the same? But before that, between these two, you can't do that, because that's where you are actually designing the logic. The first question that I came up when I put the gray counter picture was that there is another way of doing that, right. From 0 0 I was going to 0 1, someone pointed out I could have gone from 0 0 to 1 0, right. So you have design choices. Now and these choices are all going to give you circuits which are logically different, they are not the same function, right. So there at these levels you cannot do equivalence checking. When you are building the RTL, you have to make sure it is functionally correct, and then once you are decided with that, your logic has been frozen. Now you are not going to optimize the way you do the design anymore. It is only about optimizing the number of gates, the number of states, preserving the Boolean equivalence between the functions, right. So that's what is checked with here. That's the verification problem here. And then you go from that to the layout and the mask. So this talks about some of the pieces of the verification puzzle. So at the top you have architecture validation, which I just now talked about that. You have microcode validation, which actually validates the micro architectural instructions and their correctness. We have timing validation, which I don't think I'll have time to talk about. We have protocol validation. These processors, they communicate, the modules communicate between each other using different protocols, right. So the processor to the memory and the other I/O. There are certain protocols, and you have to make sure that your modules are compliant to that protocol. So that's a major problem. Then power validation. There are new power formats that have come up called UPF, CPF, etc. These power formats allow you to specify the kind of power management that you want to do. So which one you want to switch off at which point of time, you can encode that using state machines and functions. And then the problem of power validation is to make sure that the circuit actually does that and meets the power requirements of the design. So when we talk about functional verification, we want to make sure, is the implementation correct? How do we define correct? So the classical way of defining correct is to check whether simulation result matches with some golden output. Right? So we simulate the design and then check whether it matches the intended output. Now more recently we have formal methods which have come into the design verification area, where we look for equivalence with respect to a golden model, and the equivalence is exhaustive, within which we have formal property verification, where we check certain properties of the design and then make sure that it holds on the design correctly. Okay. This is the typical simulation flow. So you are going to learn in this course how to write what is called a test bench. A test bench is a program which includes the design as one of the units and then drives inputs into the design. So it's a program which generates inputs for the design, and then the simulator simulates the test bench along with the design and checks that how the circuit behaves under those inputs, reports back that to the test bench, and the test bench based on that decides what should be the next inputs, right. So for large designs, people also develop what is called a test plan. So that test plan actually talks about what are the items that needs to be verified, and the test bench along with the test plan generates the stimulus for the simulation, that are the inputs for the simulation, and the simulation output is monitored by certain coverage monitors which takes into account whether all kinds of behaviors have been checked, which behaviors have been checked, which have not been checked, and then that feeds back again into the simulation environment, and this simulation runs and runs and runs. When you have errors, you go to the debug, you do a bug tracking. When you identify the bug, you fix it in the design, then come back and then do the simulation again and again, right. Now what is happening here is that people have made these test bench languages more richer. So if you look at the system Verilog test bench language, you will be given some exposure to that. You will see that it's a language which has features of modern programming languages. So you can have processes, you can have fork join, you can have pipes to communicate between two processes. So it's a completely programming language kind of stuff, right. So it's a very useful thing with which, and in addition to that, you will have coverage monitors and assertions to check different behaviors, and it supports things like layered test benches. You can model the different basic activities like you have some bus transfer. So you can write a code for bus transfer, and then you can write a higher level test bench which says that I will do a single transfer 5 times and then do a bus transfer, right. And then you can actually call that entire transaction as one entity, and it's going to execute in the lower layer. Right. So just like in networks you have several layers, in this also you can have several layers, and that actually enables you to design test benches for large designs. This is a slide which talks about the advent of formal methods in the electronic design automation. So as I said, that from the register transfer level, gate level and transistor level, people do logical equivalence checking. At the higher layers, what you do is property verification, which is alternatively called model checking. Now this is an area which has seen tremendous growth in the last couple of decades. So temporal logics was introduced by Amin Nueli, who is a very renowned scientist from Israel. So he won the Alan Turing Award. Are you familiar with the Turing Award? Computer scientists definitely are, right? So it is the highest award in the computer science domain. The temporal logics were adopted into languages for specifying circuit properties, and the body which did that is called Accelera. Accelera is the body which fixes language standards for things like Verilog, System Verilog, Verilog AMS, etc. And then these standards were integrated into System Verilog within 1.5 decades. You know, that's a enormously small amount of time for something which is so much theoretical to be adopted in practice. And within no time, there were tools from the academia. This is a CMU tool for model checking. This is the Berkeley tool for model checking, and then you have the industry tools which have come up also within a very short period of time. Magellan is the tool from Synopsys. IFB is the tool from Cadence. I believe that you will be given some exposure to new SMV. We also have Magellan in the lab, so later on you can, if you want to get exposed to that, you can use it. And this year, the people who actually developed the original algorithms for model checking, namely Ed Clark from CMU and Emerson from University of Texas at Austin, they received the Turing Award jointly this year for this work. Let me give you an example of what this property verification is about. Suppose we have an arbiter, and we want to say that in this arbiter there are 2 request lines and 2 grant lines. We want to first say that the grant lines are mutually exclusive. So we are not going to grant the 2 lines at the same time. So this property says always I will have not grant 1 or not grant 2. So one of the grant lines will always be low at every point of time. So G says always globally I have not grant 1 or not grant 2. These are some other properties. Whenever R1 is asserted, G1 is given in the next cycle. So always if I have R1, that implies that in the next, X stands for next, in the next cycle I will have G1. If R1, then in the next cycle G1, and this must hold always. Always if I have not R1 and R2, which means that R2 is the sole request, then G2 comes in the next cycle. And the final requirement is when none of the requests are high, that is when not R1 and not R2, then in the next cycle we should have G2, which means that the grant will be parked on G2. The default grant should be G2, right. So these are the 4 properties, and let us say that the requirements of the design is a design which satisfies these 4 properties, right. Now somebody has come up with this design. The verification problem is to find out whether these 4 properties, the 4 properties that you see here, this one, this one, this one and this one, whether they hold on this design. So will this hold on the design? Yes, because whenever you see, whenever R1 is high, then in the next cycle G1 will be high, but G2 will be low, because this one is going to drive the AND gate to low, so G2 will be low. So whenever R1 is high, only G1 is high. When R1 is low, then G1 is low, right. So 2 of them cannot be high together at the same time, right. Whenever R1 is asserted, G1 is given in the next cycle. That is true, because R1 is asserted, then G1 is asserted in the next cycle. When R2 is the sole request, G2 comes in the next cycle. So R1 is 0, so this is 1, R2 is 1, so in the next cycle we will have G2. When none of them are high, then in the next cycle we will have G2. If this is 0, this is 0, next cycle, no, this one is not holding on the design, right. So that is a violation. This is what the property verifier will tell you. It will tell you that look, this one is not being satisfied, and it is not only going to tell you that, it is also going to tell you that it will not be satisfied, and to check that it is not satisfied, you drive R2 to 0 and R1 to 0, and then you see that this is going to get violated. So, it is going to produce a counter example to demonstrate that it does not work, right. So, this is what is property verification. Property verification is studied in two different contexts. One is dynamic property verification, where you check whether the properties are being, whether they are holding during simulation. So, you see this is the device under test, this is the test bench. Okay, so, I have the test bench here, and then this is the property checking part. So, I write down the properties in a language, and the language that you saw just now is a logic called temporal logic, but there are nice languages which extend Verilog and VHDL to enable you to write these properties, and then the simulation engine is going to check those properties as the simulation proceeds. So, it is going to keep track that when R1 is going high, when R2 is going low, and then it is going to check all those properties during the simulation run, right. That is one way of doing it. The other way is the formal property verification way of doing it, where you write the properties, you have this, and you have this static checker. This checker is going to take your circuit and take the properties and check this exhaustively. What is the difference between these two? Here the property is getting checked only over the simulation run. Now, simulation is not going to test all inputs, it can't, because there are too many different input combinations. So, you are only going to check the properties over those inputs where the simulation has exercised. So, in the previous example, if the input R1, not R1 and not R2 is not driven by the simulation engine, then this violation will not be detected by the simulation. But the formal engine is going to take care of all of that. It is going to mathematically prove that this device under test satisfies these properties under all possible inputs. Okay, so, that is the difference between the formal and this. But the formal thing does not work for large designs. So, people look at mixed kind of approaches. I will skip through this slide. This talks about that what is the flow that people actually use in practice. They use a combination of simulation and formal verification. I will conclude this. This is a group which I personally look after. This is the formal verification group, the verification group in the computer science department, which is also affiliated to the AVLSI lab. So, we work on verification problems across the spectrum. So, we work on digital design validation with Intel and Synopsys. We work on analog validation with National Semiconductors. We work on automotive control system verification in the problems that I was talking about with General Motors, which is a automotive company. We work on web interface verification. Web interfaces also interact with each other. You have to make sure that the transactions are correct. Otherwise, if you do an e-commerce transaction using a credit card and something goes wrong, that can be a bad thing. We work on again digital design verification with IBM. We used to work on processor verification with Sun, and this is a small EDA company with whom we have several research partnerships, and this is the family. So, maybe one day we will see some of you also in this family. Okay, so thank you. That's it for today.